So chapter 4 is these higher order differential equations. So we've been sitting around doing first order differential equations. So now we get to do higher order differential equations. And maybe some of the theory we'll start with second order, but it kind of applies to third or fourth or fifth order DEs. You know what that means, right? What does that mean? Second order, third order? Higher order derivatives, right? A y double prime, a y triple prime, a y quadruple prime in the problem. Yeah, sounds great, I know. But they are actually kind of nice once we get going. But we start off in 4.1, I guess, and what the book does a lot to you, and I'm going to start doing this too, is that is try to verify some stuff. So watch this. Here's a higher order differential equation. Y double prime plus 3y prime plus 2y equals 0. So this is actually a fairly nice one, and then I'm going to tell you that y equals, I'm going to say that y1 equals e to the negative 2x is a solution. Well, so I'm saying it's a solution, and I guess I'm going to say, can you please verify it? And we did some verify problems back in chapter 1 and 2. You know how to verify this, I guess. What would you do?
Derivative.
Yeah, I mean, if we want to verify that he's a solution, and I'm calling him y1 because I might have another one here in a second. But if we're going to verify he's a solution, then yeah, I should be able to take his derivatives, plug them in, and he should work. Let's just do it real quick. Y1 prime is negative 2 e to the negative 2x, and y1 double prime
4 e to the negative 2x
is a positive 4 e to the negative 2x. Okay, so when I plug these in, it should work, meaning we should have a true statement. When I plug this in for y double prime, that's that. Plus 3 of these y primes, and y prime is negative 2 e to the negative 2x. And then 2 regular y's, okay. So then positive 2 of the regular y's, okay. So is this true? Well, it looks like I have 4 of these e functions. I have negative 6 of these e functions, and then positive 2 of these e functions. If I add these up, they are like terms, and you indeed get 0 equals 0. So, cool. Verified. We verified that this was a solution. Okay. Listen, here's the funny thing about higher order DEs. There's kind of more than one solution. Here's another one. I'm going to tell you that this is a solution. Y1 equals e to the negative x. I think he's also a solution. Let's try to verify him real quick. Y prime would be negative e to the negative x, and then y double prime.
e to the negative x.
Oh, by the way, I shouldn't have called him y. I should call him y2. Sorry, I called him y1 again. Sorry. That's y1. Let's call this guy y2. Subscript 2. Y double prime of subscript 2. And what did we say? Y double prime was positive e to the negative x. The chain will keep spitting out a negative sign there. When we plug this in to the DE, I think we'll verify that he's also a solution. I'll just try it. Y double prime, that's this. And then 3 of these y primes, that would be 3 of these e to the negative x. But there's a negative sign on that. And then there's positive 2 of these guys. Okay, positive 2 of those original y's. Well, does that add up?
Good.
I'll be darned. It sure does. 0 equals 0, which indicates, yeah, we verified that. So the truth is, we verified these 2 solutions here. And then what we do is we form the general solution from these 2 solutions. So the general solution to this DE is, I'm going to say this, is a linear combination. It's called a linear combination of the, I'm going to use the letter n here, but in my example, n is 2. We had a second order DE and we found these 2 solutions. But this theory sort of applies to any n. If I had a third order DE, I think I'd have 3 solutions. If I had a fourth order DE, I think I'd have 4 solutions. So I'm going to say the general solution is a linear combination of the n, listen to this now, linearly independent solutions. Jesus. The general solution is a linear combination of the n linearly independent solutions. So in my example, it was a second order, n was 2, and I had 2 linearly independent solutions. Now I've got to define that language for you. I'm using some language I haven't defined yet. That might not be the best teaching technique, but we'll get there. And I also have to define what a linear combination is. Well, here we go, you guys. The general solution, which we call y, is this. It's C1, Y1. Here, I'm just going to talk in general. C1, Y1, and plus C2, Y2. When you take your solutions, Y1 and Y2, multiply them by constants and add them up, that's called forming a linear combination. Multiplying them by constants and adding them together is a linear combination of y1 and y2. And the general solution is this. So here it is. It's c1 e to the negative 2x plus c2 e to the negative x. That's the general solution. Oh, and by the way, perhaps I should verify this. Well, I don't know. I'm already a little sick of verifying. Verifying is kind of fun, but it's kind of... You knew it was an answer. You just take a couple derivatives, plug it in, and watch it work. So I verified him. Separately, but the truth is now, this new general solution should work also. And by the way, it should work with the generic C's in there. The C1s and the C2s. If we did a Y prime and a Y double prime on this guy, and plugged it in, it would work also. Maybe you can sort of see that. I mean, again, you just saw each individual one work. Maybe you can imagine how this linear combination of those two things would also work. But you could actually just go through it and try it. I'm not going to do it, though. But you could take a couple derivatives. When you're verifying, you would spit out a negative 2, I guess, but don't let it absorb into that C. Keep these C1s and C2s separate, and then everything should work. He will verify as the general solution. So it turns out, you guys, I mean, and what happens in 4.1 is they haven't taught you how to solve these DEs yet, and they're trying to get you used to solving them, and so they ask you to verify some stuff. They give you the solution and verify some stuff. But when we do start to solve them, this is what we're looking for. We're looking for we're looking for n linearly independent solutions. Once we find all these independent solutions, then we'll write the general solution like we did. So we gotta learn what this means. What does it mean to be linearly independent? So here comes this is a mathematical definition. So here comes a definition, and actually the definition is for linear dependency. And the definition is this. It's in the book, but here's my kind of loose version of it. It won't be too loose. A set of functions, y1, comma, y2, comma, ... yn. A set of functions is said to be linearly dependent, is said to be linearly dependent. That's what we're defining. On some interval I, you know what I mean by an interval, right? Maybe negative infinity to infinity, maybe 0 to infinity, maybe negative 5 to 5, some interval. A set of functions is said to be linearly dependent on some interval I. Watch this. If there exists constants, oh boy, constants C1, C2, ... Cn. Here's something about these constants. They're not all 0. Not all of them can be 0. Such that C1 times Y1 plus C2 times Y2 plus ... Cn times Yn adds up to be 0. That's the definition of a set of functions being linearly dependent. It's kind of tricky. It's definitely mathematical type of definition. Higher math is kind of like this, by the way, in case you want to switch majors. I mean, it's definitions and theorems and a lot of writing and a lot of well-defined ideas. What I try to do as a math teacher is try to help you interpret what does this mean in a little more English language, a little less math language maybe. By the way, what's the definition for linear independence? Because that's really what I'm looking for. I'm looking for linearly independent stuff. But the definition they're giving me is linearly dependent stuff. Here's what the definition, it says, if no such constants exist, if we can't find these constants, if no such constants exist, then the set of functions, y1, y2, comma, ... yn, is said to be, in other words, if it's not dependent, you know what it is? It's independent. Linearly independent is the phrase. By the way, don't put a whole lot of stock in that word linear. I'm struggling myself with, and I mean, we're definitely dealing with all kinds of functions. They're not linear functions. They're not lines, okay? They're any kind of functions. Let's play. This is interesting. Let's try this. So here's a couple of functions. Y1, so we're going to spend a little time on discussing this theory. So here's a function. Y1 is an x, and Y2 is an x squared. All right, well, according to this definition, I'm not too worried about the interval, actually. I'm not too worried about the interval. What I'm more worried about is, can I find these constants? Does there exist constants such that if you multiply each constant by the function, somehow you can add this up and get 0? Like, I mean, is there some number times x and then some number? I mean, can I find these constants? This is what I'm looking for. Can I find a C1 and a C2 such that when you multiply them by each of the functions, I mean, in this case, we only have 2 functions, thank God. Can we find constants that make this happen?
No. They both have to be.
Okay, you could say they're both going to be 0, except if you read the definition that we're not allowed to do that. Yeah, we can't let them all be 0. We're allowed to let some be 0, but we can't let them all be 0. So is there any constants that would make this happen? And you're saying no, huh? Okay.
1 over x and negative 1 over x.
Oh, they got to be constants.
Oh, yeah.
Yeah, I got you. Yeah, okay. So they got to be constants with no x's in them, right? No variables in them, right? So, no.
Then it's learning.
So since no such constants exist, so no way to find a C1 and a C2 that make this happen. Therefore, these are linearly independent. These functions are called linearly independent. Now we just went through some formal definition and some formal math there. You know, you might start coming up with your own kind of informal ideas. Based on that one example, you might be able to come up with some informal ideas like what? Do you have any ideas?
They have to be the same power.
Yeah, kinda.
Base.
Or that makes me think of algebra when he said same power. What do we call that?
Like term.
Like terms.
Terms.
Yeah, maybe they got to be like terms. See, it is kind of like that. I really can't. Let's do another one. Let's do this one. y1 is 3x minus 1. That's a function. y2 is 4x. And y3 is 8. Now, those are three different functions. Are they independent or dependent? Well, can I find constants, not all 0, such that C1 times Y1, C2 times Y2, and C3 times Y3 somehow add up to 0? I'm going to write that. Can I find some constants? And I don't really have a good method, you guys, except, well, I might have a method, I guess. Is there any way to make this come out to be 0? I got to find the right constants. Let's just start with this. If we got to get those x's. We got to get rid of those x's. So maybe.
Just go for the C1 and C2 first.
Yeah. So maybe let's. Any ideas? Like maybe let C1 be a 4, because that would give you a 12x. And then C2 could be a negative 3. Is that making sense to you? I'm looking for, my method is just to kind of play around and feel this out. But you guys are onto it. So now I have a 12x and I have a negative 12x. So I will get rid of my x's. But what will I be left with? If C1 is a 4, I'll have a negative 4 here. And then I'll have to, then I just need to pick the right C3 and I should be able to do it. Yeah. If C3 is a 1/2.
Yeah.
Are you guys okay? So we got it. Woo! So, what's the deal? We found these three constants. What does that mean?
Dependent.
Oh, they are dependent. They are dependent. Yep. They're dependent. It's the set that you call dependent. You don't really say one of them is dependent on another one in a way. You don't. It's the whole set is dependent on each other, I guess. Is dependent. Yeah, that was kind of fun. It's kind of fun. Math game. Try to find these constants. If you can, they're dependent. If you can't, they're independent. But, to just loosen up the language a little bit, it is kind of about being a lot alike and being kind of different. That's kind of what it is, except no, you won't read that in your math book. Kind of a lot alike, kind of different. Math is a well-defined language with well-defined definitions. But it is kind of like that when I interpret it for you. If the functions are enough alike, I guess they're dependent. If they're different enough, they can be considered independent. But you might really need this full-blown test. I think, right off the bat, 2 or 3 weeks from now, when we take a test, we're going to be solving all kinds of DEs, but if there's a question from 4.1, it's probably this question, or this question, or, I mean, it's something like this. Prove that these things are dependent or independent using this definition. I might even give you this definition. Yes?
For that, if the negative, like the 3x minus 1, if minus 1 was not there, couldn't you possibly do that? I think that would be impossible.
Yeah, okay, that's a decent question. So if we just change this question slightly by making the minus 1 be not there, right? He's just saying make that not there.
C3 can be 0.
You can.
Not all of them.
Not all of them.
Oh, so now you're saying we could let C3 be 0. You are allowed to let some of these constants be 0. The only rule is not all 0. Yeah, I got you. Okay, good job. Right. I mean, that would be trivial. Let's make them all be 0. So anyway, that's the only rule, kind of. So you're allowed to have plenty of zeros, actually, but just not all 0, right? Okay, so I got you. They would still be dependent. What if that 8 wasn't there? What if I just didn't have? What if I just didn't have that guy? What if we just had those two guys? You know, they're kind of alike because they are linear functions, but
that 1 there.
But with that 1 there, it makes it different enough that I can't, huh? So now they are independent. Yeah. Yeah. Here's just to be, you know, the classic tricky question here is this one. Watch this one. Sine squared of x, cosine squared of x, and 17. What about those three? I mean, look at them. I mean, see, so after I sort of taught you the layman's way of thinking, I would walk in here like a layman and I would say, dude, those things are different, man. Sine squared, man. These are totally different. They're totally different. They're independent.
Negative 17 for C1, C2.
But I'm wrong.
Yeah.
Because of the wonder of trig identities, all kinds of weird crap can happen with trig identities.
C1 and C2 can just equal 1, and then you can have 1 over 17.
Okay. You guys are too fast for me. Hold on. You're saying, due to the wonders of trig identities, you're saying,
Let C1 and C2 equal 1.
let C1 and C2 both equal 1,
C3 is
because then this will add up to be 1, because sine squared plus cosine squared is 1, and then you're saying, well, let C3 be a
negative 117.
negative 1/17. That's my favorite number, by the way. You're right. With those three numbers in place and the wonders of trig identities, we would now call these dependent. Even though they look kind of different, it looks like different guys, they're dependent. I mean, I guess when you see a sine squared and a cosine squared, you should think constant. It's a 1, you know, and so therefore it's related to this constant. There are more than one right answer when you find these C's. In fact, it turns out, I think any multiple of these answers kind of work. It's almost like vectors. In other words, this 4, negative 3, a half worked. What if you multiplied them all by 2? 8, negative 6, and 1, I think also work. I think any multiple of them work. So what were you suggesting? Maybe
Multiply by negative 1.
Yeah, or multiply by 17. Let's use 17, 17, and 1, or negative 1. That would work, right? There are multiple answers when you can find a set of constants. I think there's not just one set, but any set you find will be a multiple of the other one. So it's okay. There's another way to test for linear dependence or linear independence, and it's called the Wronskian. Let's try it. I might try it with this. Y1 is e to the x. No, y1 is e to the 2x, and y2 is e to the negative 3x. Now, by the way, what do you think about those guys? I mean, now we could go through our official definition. I'm going to teach you another way called the Wronskian, but you're getting a feel for this already. What's your feel for this? Independent or dependent?
Independent.
Okay. Maybe you're thinking about this method because this method works pretty good. Or maybe, you know, I don't know. On one hand, you might look up there and say, hey, those are both exponential functions. Exponential functions are kind of the same, man. Maybe they're dependent, but that's kind of stupid. Exponential functions with different arguments, a 2x, and these are definitely different terms. They're not like terms. And they're different functions, and they are independent. You're right. If that's what you thought, you're right. They are independent. Watch this. The Wronskian proves this. The Wronskian is a and I like to pronounce it Wronskian for some reason. It's the Wronskian. It's when you do the Wronskian of a set of functions, you do this determinant. And I'm going to just do it for these two functions, although I'm going to just do it. Hang on. I'm sorry. I'm going to do y1, y2. What if I had three functions? Here's how you do it if you had three functions. You write your functions across the top row of the determinant. The next row is y1 prime, y2 prime, y3 prime. And then the third row is y1 double prime, y2 double prime, and y3 double prime. And when you finish doing this determinant, good luck. If the Wronskian of this set of functions is not 0, then that set of functions is independent, I think. I better read this. You guys are supposed to be reading just ahead of me. Yeah. Let's see. When the Wronskian is not 0, they are independent. Right. Okay, so I'm sorry. When I did this determinant, I did it for three functions. What if it was four functions? It would be a 4x4 determinant. If it's three functions, it's a 3x3 determinant. If it's five functions, it's a 5x5 determinant. Maybe you see the pattern. Listen, to do this specific example, it's just two functions. And so it would be a 2x2 determinant. And it would be this. The Wronskian would be, what do I do? On the top row, I put the functions. Yeah. And then on the next row, I put their derivatives. And the derivatives involve chain rules, right, you guys? And then you got to do the determinant. You might need some advice on that. When you do a 2x2 determinant, it's real easy. You multiply this and subtract the multiplication of this. Don't get those diagonals wrong, but anyway, here I go. If I multiply this, I get negative 3 e to the 5x minus the multiplication of this, which is, oh, wait a minute. I made a mistake. This was a negative 3x, you guys?
Yeah.
And so this is not 5x. I made a mistake. It's negative 3 e to the negative x minus 2 e to the negative x. When you add that up, it's negative 5 e to the negative x. And guess what? Maybe you know exponential functions are never 0. This is not 0. This is never 0. And therefore, if it's not 0, if the Wronskian is not 0, those functions are independent. Yes?
What if you have like 4 functions and then one of your functions is something you can't take 3 derivatives of? What if it goes to 0 on y?
Yeah, then you might have some zeros in your column.
So you'll just throw another 0.
And those are nice. when you do determinants, it's nice to have zeros in the column, but yeah. Maybe we should do another example. I got, some more exciting ideas for you. What if we tried these functions? You ready? I'm going to make up another one. Y1 is 3x squared plus 4. Y2 is x squared minus 2x. And Y3 is x squared plus x plus 1. So, now if you had your choice, on this test, which again is 3 weeks away, but I think I might have a couple of these questions for you. I might have one that says use the definition, which I just erased, which is find your C1s and C2s to prove whether they're independent or dependent. But I might have another question that says use the Wronskian to tell whether they're independent or dependent. So I might have a couple of these questions, just like we're doing right now. Anyway, if you had your choice, you might not have your choice on the test, but if you had your choice, I don't know about these. These are tough. I mean, I know they're all quadratic. They're all quadratic, kind of makes me think they're the same, which kind of makes me think they're dependent. But as you've seen, this can be a misleading little, that line of thinking can be misleading. So I could play around and search for the C1, C2s, and C3s. Let's just do a damn Wronskian. You ready? All right. So that means I'm doing a big 3x3 determinant. I'm sorry. I mean, I'm so sorry. Not really. Wow, I gotta do, the derivative of this is a 6x. The next derivative is a 6. You guys okay with that? I need derivatives. Here's what I need. This is a 2x minus 2, and then a 2. This is 2x plus 1, and then a 2. So that's it, right? My 3 functions, my 3y primes, my 3y double primes, and I've got a 3x3 determinant. How do you do a 3x3 determinant? Do you guys know?
You do smaller determinants?
There's a couple of ways. Good. You're kind of right. Especially if you're in Cal 3 and you kind of remember the cross product, is a 3x3 determinant. When we do a cross product, and we do it by expanding by minors. We would grab one element and do a little mini determinant, his little minor mini determinant. Then we'd grab another element and his minor. Here's another way to do it. Watch this. This is sort of an algebraic shortcut, maybe. It's not that short. Copy down. See, the truth is, you got to multiply this diagonal, and then you got to but there's more than one diagonal. You got to multiply this diagonal. Watch this. This diagonal. Now, where's the third element of this diagonal? Right here. And then this diagonal. Now, where's the other 2 elements for this diagonal? Right here. So it's this diagonal. It's all those 3 diagonals multiplied and added up minus the other 3 diagonals, which is this one, this one. Now, wait a minute. Where's the third partner to this diagonal? Right up there. And this diagonal, where's his third partner? Right. That's it, you guys. Now, what they taught me back in 3rd grade when we did this was here's what they taught me. Oh, copy down these first 2 columns. 3x squared plus 4, 6x, and 6. And x squared minus 2x, 2x minus 2, and 2. Copy down those first 2 columns, and then you can grab those diagonals I described are this diagonal. See, there's the 6, right, you guys? Remember? And then this diagonal. Those three added up, multiplied and added up, minus the other three. Where's the other? Hang on, let's do one thing at a time. Here we go. Oh my God, I gotta multiply all that? 3x squared plus 4 times, if you don't mind, I'm gonna multiply that and call it 4x minus 4. Is that okay with you? These two times this one, you guys okay?
Yeah.
Okay. Next, plus the next diagonal. X squared minus 2x. What's that going to be multiplied by? This thing. What am I going to call this thing?
12x plus 6.
I am. I'm going to call it a 12x plus 6. Plus, what's next? Oh, this one. Oh my God. That's a 12x. If you don't mind, that's a 12x times that trinomial up there. 12x times that trinomial up there. Awesome. It's that diagonal minus, see the big minus sign? So damn big it looks like an equal sign. It's a minus sign. Minus the other three diagonals. Where's the other three diagonals? This one, and this one. All right. Here we go. I better put brackets around this.
12x.
12x minus 12 times that. Oh my goodness. I mean, I thought when I hit differential equations I could get rid of foiling, didn't you?
Yep.
4x plus 2. That's a 4x plus 2 times 3x squared plus 4. And 12x times that thing. So I got to do a bunch of major foiling, or you do. Somebody does. And combine like terms and add this stuff up and see what are we hoping to get. If it's not
Say 0.
if it's not 0, they're linearly independent. If it is 0, I guess they're dependent, huh? Okay. On your mark, get set, go. I'm gonna get a 12x cubed. Might be fun just to do this up here. Wow. In fact, that might be fun. Hold on a second. I'm going to do it up here. I'm going to get a 12x cubed, negative 12x squared, a 16x, and a minus 16. Wow. What about this? That's a 12x cubed, 6x squared, negative 24x squared, and a negative 12x. Wow. And then this last one is a 12x cubed, plus a 12x squared, plus a 12x. Hey, help me out. What is that? It's just that top. Now I want that top cleaned up, if you don't mind. What is that? That's a 36x cubed. Positive 12. This 12x squared. Oh, hang on. Cancels with this 12x squared.
So negative 18x squared.
But I got these two. That's a negative 18x squared. Okay, thank you. What about my x's? I got a 16x minus a 12x is a 4x. Plus that's a 16x, I guess. Any numbers? Any plain old numbers anywhere? Right there is a negative 16. I hope I did that right, you guys. Minus, I got to foil all this out, huh? Okay, on your mark, get set, go. This makes for exciting video, by the way. Get set, go. 12x cubed plus 12x squared plus 12x minus 12x squared. Wow. Minus 12x. Wow. Minus 12. That's all that junk. I think I did all that, you guys. Moving over here, there's a 12x cubed. There's a 16x. There's a 6x squared, and there's an 8. moving down here, there's a 12x cubed and a negative 24x squared. Woohoo! What do I have now? These guys are gone. I have a 12x cubed, another 12x cubed, I got a 36x cubed. What else do I have? A 6x squared and a negative 24x. I got a negative 18x squared. I'm freaking out. What else do I have? What about my x's? Plain old x's. A 16x? I think I got a 16x. What about my plain old numbers? Where's my plain old numbers? Negative 12 and an 8. I think I got a negative 4. This is amazing. When you subtract these, it feels like it's going to be 0, but it's not. The 36x cubed cancels. The negative 18x squared is going to cancel. The 16x is going to cancel. But you get a negative 16 plus 4. The answer is negative 12. And guess what? Negative 12 is not 0.
It might have been just better to say it hopefully doesn't equal 0 at the beginning.
What a
I'm
pain.
expecting all the way to 2 to equal 0.
Good. So what does that mean?
It's linearly independent.
Yeah, they're independent. Even though they're all quadratic, they are independent. Maybe I don't like this Wronskian. Maybe searching around for the C1s and C2s and C3s might have been a better method for this. But I wanted to do a 3x3 and torture you just a little bit. But that's our conclusion. Linearly independent.
I would literally just keep searching though. Like if I didn't find something, so this is.
So this kind of is more conclusive than
conclusive.
searching for C1s and C2s, right? Although there's a point where you can convince yourself, logically maybe, that there aren't any, but
I mean, once I got to that point down there, I would kind of think that I just did my math wrong.
well, I know. I could have done something wrong too, but let's erase it before anybody finds out.
Not even recording it or anything.
Wow. All right. Listen, let's do something else. I think I just want to do a problem in 4.1 because when you guys try to do this homework, it might look a little different than some of the stuff I've been doing here today. So I'm in 4.1 and I'm gonna grab this problem 14 and I'm gonna do some of it, okay? And here's what it says. It says y equals c1x squared, y equals c1x squared plus c2 x to the 4th plus 3. So that's a y. I mean, that looks like a solution. That looks like a general solution to a DE. They actually tell me that it's the solution to this DE. This DE. X squared y double prime minus 5x y prime plus 8y equals 24. That's a differential equation. They gave me the solution, and what they really want me to do, I need to read the directions, but there's a part A, B, C, and D here, and in part A, they give me this. Actually, I want to do part B, sorry. Part B, they say this. Y of 0 is 1, and y of 1 is 2. This is, all right, so then what are the directions? Listen, the directions are, given the 2-parameter family is a solution of the indicated differential equation, well, that's nice. So they're saying this, they're calling this a two-parameter family when it has these two constants. They say it was given that it's a solution to this DE. If they didn't really say verify it yet, if they wanted you to verify it, how would you verify it? Take two derivatives, plug the second derivative in there, plug the first derivative in there, plug the original function in there, and it ought to work. Right? I mean, that's how you verify it. And you can do it with these general C1s and C2s, and it should work. We could take a first derivative and a second derivative, plug them in there, and it should work. But they didn't really say to verify. They said, given that, it says, determine whether a member of the family can be found that satisfies what they call these. They call these, what do you call these?
Initial
value.
Yeah, good. We call these initial values or initial conditions. Hang on. All of a sudden, your book calls them boundary conditions. This is very subtle. Not a big deal to me, but the book seems to make a big deal about it. Listen, here's the deal. Here's what makes them different. Initial conditions are all about what might be happening initially, like y of 0 equals 1. They did say that. And then maybe y prime of 0 equals 3. These are things about what is happening initially. Do you get it? When t is 0 or x is 0. All right, so technically, these aren't initial conditions because why?
There's a y of 1.
Yeah, because it's like a boundary condition. Now I've got some curve, and what they're saying is when x is 0, y is 1, and then there's not another initial condition, but there's another condition, and it's over here when y is 1, oops, when x is 1, y is 2. You guys okay? I mean, those 2 points are like, they call them boundary conditions. It's subtle, not real important to me. Let's move on. What am I supposed to do, though? Use these conditions to see, plug them in and see if I can get, I use these to find C1 and C2, right. I use these to find C1 and C2. I use them just like initial conditions, but technically they aren't called. They're called boundary conditions. Hey, let's try it. By the way, what's kind of nice is neither one of these is about the derivative. I don't need a derivative for these conditions. I would need a derivative for these conditions. So all I got to do is try to plug these in. Now remember what their question was. The question was, is there a solution that can you find a solution that meets these conditions? So we may not be able to find an answer. I don't know. Let's see what happens. If you plug in a 0 for x, your y should equal 1. Okay, here I go. Plugging in a 0 for x, holy shit, I get that. Well, that sure looks suspicious. Let me try this. If I plug in a 1 for x, I get a 2. If I plug in a 1 for x, I get a 2. Okay, so it's C1. That's a C2 plus 3, and it equals 2, right? If you plug in a 1 for x, it equals 2. That's what that says. Well, all right. So, but that accompanied with this would tell you that the answer is no. We cannot find a function. This is a family of solutions, and we cannot find a member of the family that meets these conditions. No, we can't. Right. What was part A? Part A was y of -1 equals 0, y of 1 equals 4. What if I just change it? Hang on just a second. Part A. Y of -1 equals 0, y of 1 equals 4. Again, two boundary conditions. Again, can you sort of see there's nothing initial about this maybe? We're not doing this at 0. So a couple of boundary conditions. Anyway, we'll see what happens on this one. Can we find a member of the family that satisfies this one? if we plug a -1 in for x, we get a 0. Let's try that. Plugging a -1 in for x gives me C1 and C2 and 3. You guys okay with that? That was kind of easy, right? Plug a -1 in for x, and that's what you get. Plug in a 1 for x, and you get C1 and C2 and 3. You get the same thing, but now it equals 4. That's interesting. I wonder if I can solve this system of equations. It is just now a system of 2 equations, 2 unknowns, but did something feel weird to you?
No.
It does feel kind of weird that they have even, that this equals 0 and at the same time this equals 4. But there are 2 variables. Maybe I can, maybe not. You can solve and substitute. You can, let's see, what is C1? C1 is negative C2 minus 3. Is that okay with you? Right? I move these guys over. And then what if I go plug that in for C1? Oh, I see what happens. Yeah. C1 is a negative C2 minus 3 plus C2 plus 3. The C2's cancel, that's the main thing. The 3's cancel, that's kind of insignificant. We get 4 equals 0. Well, another false statement. When you get these false statements, it means the answer is no solution. There is no C1 and C2. All right, enough of that. Enough of that. Well, I'm debating in my brain. I'm debating what I want to do right now. All the good action is up in 4-3, but between now and 4-3, there is some tough stuff in 4-2. What do you guys want to do?
All of it.
I shouldn't have asked you. 4-3 is where the good stuff starts happening. I'm going to have trouble getting there today. You might have to wait till Thursday. On the way to 4-3, to the really good stuff, let's pass through 4-2 here. 4-2 is a funny little tough section. It's called reduction of order. It's funny. I'm going to I assigned about 3 or 4 problems in this section is all. And I'm actually going to do one. I'm going to do number 4 out of the book. Number 4, they give me a DE. Y double prime plus 9y equals 0. We're doing these higher order differential equations. What's funny is they give me one solution. You're given one solution. Here it is. But anyway, you're given one solution and the directions are find the other. And the method for finding the other one is this reduction of order method. So here's this one solution that's given. Y1 is sine of 3x. Okay, so they're saying find the other one. Y2. Here's what we do. We assume that the other one that we're looking for, Y2, is going to be some function of x, I'm going to call it u of x, some function of x times this one. Now that's kind of a strange assumption. I wonder if I can talk you into it. One of the things we learned the first 45 minutes, an hour here, is that if there is going to be a second solution, it's going to be linearly independent from the first solution. It's got to be independent. So it's not a constant multiple. That's why I called this a function of x. Like maybe this is an x sine 3x, which would make it independent from that guy. Maybe it's x squared sine x, which makes it independent from that guy. I mean, in the end, I'm going to be trying to find what this u is, which will give me my second solution. But I'm assuming it's some function of x times that guy, and that will make it a linearly independent second solution. All right, you ready? If that's my assumption that he's a solution, then I should be able to plug him in and he should work. Okay, if I'm going to plug him in, I need a couple derivatives. Because this is not a constant, it's some function of x, I need to do a product rule. Y prime is, and I'm gonna lose the of x notation. I'm just gonna call this, it's u of x, but I'm gonna call it u prime times the sine of 3x plus, write down the u and multiply by the derivative of sine. What's the derivative of sine? Cosine?
3 cosine 3x.
With a 3 spitting it, so it's 3 cosine 3x. Okay, thank you. That's u prime, that's y prime. Okay, now I need y double prime. Oh my God, guess what that is? Two product rules. I ain't scared. You ready? Derivative of this one.
U double prime.
That's a u double prime times a sine 3x, that's times a sine 3x, plus write down u prime and take the derivative of sine 3x. 3 cosine 3x. Plus, now I'm doing this product rule, you guys. I'll pause and breathe a second. This product rule, I'll do the derivative of the u prime, times the 3 cosine 3x, and then write down the u and take the derivative of the 3 cosine 3x. That would be a negative 9 sine 3x. Wow. All right, I should be able to plug this stuff into the DE. This is the DE, you guys. Are you ready? Here we go. Y double prime gets plugged in for this Y double prime. Now here it is. It's U double prime, sine of 3x. Hang on. This middle term is what? There, you can add that up. That's a 6. That's okay, yeah. 6 cosine 3. It's a 6 cosine 3x u prime, I guess. And then and then the last one is a negative 9 sine 3x times u. That's y double prime. Plus 9y. Now wait a minute, what was y? U sine 3x. U sine 3x equals 0. Okay, this is awesome. These last two terms cancel. Is that what you see? Mm-hmm. The last two terms cancel. And we're trying to find u, by the way, in case you forgot. We're trying to find this u. Because if I find this u, I'll have this y2. I'm really trying to find y2. If I find u, I got it. So that means I'm solving this little differential equation now. And it's second order, and you really haven't learned how to solve second order. But the method we're going to use is called reduction of order. Here's what we're going to do. We're going to let w equal u prime. So then what's w prime? U double prime. By the way, w prime is u double prime. That just makes sense whether you understand any math or not. W prime is u double. Are you okay?
W prime is u double.
But hang on, I came up with this idea. Are you guys okay? I'm going to call, it's a substitution. I'm going to call w u prime. And therefore, what's u double prime?
W prime.
W prime. So what happens? This turns into w prime sine 3x. This turns into w. of 6, I keep swapping the order of this thing, sorry,
Integrating factor.
equals 0. Are you guys okay?
Yeah.
Now it's a first order linear DE.
Integrating factor.
I'll do the integrating factor method. Oh, great. The integrating factor method means, whoa, geez, that means I got to do e to the integral of 6 cosine 3x.
Wait, do you not need to divide by the sine 3x?
Oh, sorry, big time, yes. Thank you. That's why I need you guys. Otherwise, I'd go crazy. Yeah, he's right. He is right. What did he say?
Divide by.
To do the integrating factor method, you need this coefficient to be 1, right? Divide by the sine of 3x. He's right. Divide by the sine of 3x. That'll leave me cotangent 3x.
Yeah.
Oh yeah, that's better. Thanks. I really appreciate that. All right. Now, what do I want to do? Oh, the integrating factor. The integrating factor is e to the integral of 6 cotangent 3x, which everybody knows is something.
What's the integral of cotangent?
What is the integral of cotangent? The integral of tan is negative ln cosine. I remember that. So the integral of cotan is the positive ln of sine. I think do you think it'll spit out a 1/3?
Yeah.
It's a 6, it spits out a 1/3, and it's the positive ln of the sine of 3x. That's the integral of cotangent. I'm sorry, it's weird. And what do I got? E raised to that? Thank God. Are you guys okay? All right, listen. You know how to play this game. That's a 2, right? What are you going to do with that 2?
Bring it up.
Bring it up and put it up here, and it'll be a power. Then you can cancel the e and the log. So what is your integrating factor? Sine squared of 3x. Amazing. What's amazing is you guys know all this stuff. Somebody should just hand you a degree today.
I accept it.
That's the integrating factor? Now what? Oh yeah, you multiply through by
D
it.
over dx?
After you multiply through by it,
Yeah, d over dx.
after you multiply through by it, the right-hand side, the left-hand side becomes the derivative of the integrating factor times w. And over on the other side, I multiplied through by it. And so what do I have when I multiply through by it? I have a 0. All right, we're getting there. I'm trying to get w. What should I do? Integrate. When I integrate, I get sine squared of 3x times w equals a constant. I'm going to call it C1. Cool. I just integrated both sides. Yep. Awesome. I'm going to divide by that sine squared, and w is C1 over sine squared, but if I move that sine squared up, it's a cosecant squared. It's a cosecant squared. Wow, you guys. That's w. Wait a minute. I'm trying to get, remember what am I trying to get? I'm trying to get u. Where's w?
U prime.
Oh, w is u prime. Oh man, I'm getting close. I'm getting close. So you're saying u prime, so what's u? I need to integrate. I need to integrate? Because this is u prime. All right, so I'm going to integrate. Anybody know how to integrate a cosecant squared? I'm back to cotangent. I think I'm negative. Negative C1 cotangent of 3x. I think it spits out a 1/3
Plus C2.
plus a C2. This is so awesome. You guys just found u.
Generally. Wait,
And I'm sorry, this looks messy. That's a C1 divided by a 3 is what that is. C1 divided by 3. All right, this is great. Right at the end, choose something nice and convenient for your C1 and C2.
0.
Well, don't get too convenient. But I would. You get to
0 and C2 be 1?
I would choose C2 to be 0. And I would choose C1 to be
Three.
negative 3.
Negative 3.
because that'll make the negative sign go away, right? It'll be, okay, right, so it'll be, so now what's u? Cotangent 3x. Wow. Let's go back over here. I'm looking for this y2, if you forgot. I'm looking for y2, which is that u times the sine of 3x. And u is the cotangent of 3x multiplied by the sine of 3x. And you know cotangent is cosine over sine. So the sines cancel. We finally found y2. What is it?
Cosine.
Cosine of 3x. Somebody should have thought of that about an hour ago, or at least 15 minutes ago. I'm sort of kidding. But if that's one solution, his partner solution, it kind of, well, is this. I mean, you don't really know that yet, but I know 4-3, and when I get to 4-3, you see sines and cosines kind of come together. They come as a pair, kind of. So I sort of knew that was coming, but this is a hell of a long way around to get it. I mean, this is kind of funny, this reduction of order. I mean, don't do 20 problems. Hey, I assigned 4. Don't do 4. Try one. If you want to try one. Yes?
Can you explain why we just got to choose what C2 and C1 were?
Why do
I'm
you
confused about that.
read the book?
Wait, so we...
Let's see.
Because what if we just chose
You know
C1
why?
to be zero?
I'll tell you one thing. What we're going to do is, what we're eventually going to do here is we're going to form the general solution to the DE. The general solution to the DE is always made up. This is how I started today. The general solution to the DE is made up of those two linearly independent solutions. So they gave me one. I went through this long struggle to find the second one. Now that I got both of those, I can write the general solution as, now watch, when I write the general solution, I put a new C1 in here. I put C1 sine of 3x and C2 cosine of 3x. So I think my argument is that I'm going to introduce these new C's anyway, so I'm allowed to simplify my answer over here by picking specific C's,
Okay,
because I'm going to add some general C's into the.
Because if we chose C1 to be 0, it would have really changed everything.
Well, yeah, don't do that.
Okay.
I mean, you want the form of what's there, but you want it to make it convenient. So you don't really pick anything. You pick kind of smartly. But the justification of these are supposed to be arbitrary C's. How do I make them specific? Well, I got more arbitrary C's coming later. So maybe that's my argument, why I'm allowed to make these specific. I got more general ones coming later. All right, I'm going to quit. And Thursday,